So our plan today is to run through our regain conductivity method that we've developed at Interface over the last year with a number of our customers, and share some of those experiences, some of those case studies, and some of our technology. I'll be moderating today. I'm the CEO and co-founder of the company, and Jillian Fortin, who is our technical account manager and was a key personnel in developing this and running all the experiments you're going to see today. So she'll be running you through the technology as we go. Just as a reminder for those of you that are attending today, if you have any questions, please post them in the Q&A box, and we'll make sure we get to them at the Q&A section at the end of the webinar. Alternatively, if you have a specific question you'd like to ask, you can feel free to send us an email at webinar@interfacefluidics.com. As well, we have obviously LinkedIn and Twitter accounts where we are happy to answer questions and provide more information, as well as to stay up to date on when the next webinar is going to be posted. All the links to those are in the description here. As a brief introduction to the company, Interface Fluidics provides unique insights into the interactions and properties of reservoir fluids in order to help our customers improve operating efficiencies and enable better long-term decision-making. We have a facility in Edmonton, located at the National Institute for Nanotechnology, and our corporate headquarters is in Calgary. Our goal as a company is to make our extreme condition fluid analysis cheap, accessible, and easy to use. We've been doing this for a number of years now with customers all over the world. So we've helped our customers all the way from the oil sands in Alberta through unconventionals down in southern US, as well as conventional and other unconventional applications around the world. We offer our services in flow-through porous media for frac fluid optimization, regain conductivity, which is what we'll be running through today, SAGD optimization, as well as enhanced oil recovery, both chemical and gas injection. And on the PVT side and phase behavior side, we've developed minimum miscibility pressure and minimum miscibility enrichment measurements that we've run a webinar on recently, and we're happy to chat about, as well as wax and asphaltene appearance conditions and diffusion coefficient measurements. So with that, I will pass it over to Jillian to run us through regain conductivity. Thanks a lot, Jillian.
Perfect. Thank you, Stuart. So before I jump into the specifics on regain conductivity, it's always good to have an idea of why we decided to develop this technology. So we've identified that there's an industry shift towards produced water applications, and there's an opportunity for performance optimization and cost reduction. So because of that, we've recognized the need for a faster, cheaper, and more repeatable screening tool for friction reducer damage. This is just an overview of our regain conductivity methodology. You can see that what we are doing is we're actually replicating the frac zone on our reservoir analogs, and we're able to screen friction reducers and get a regain conductivity value using our technology. On the right-hand side, you can see a schematic of our laboratory setup. And so what we have is our microfluidic device is connected to a heating element. We're able to go up to 200 degrees Fahrenheit on this particular setup. That's connected to high accuracy flow through sensors, as well as microfluidic pumps. I'll go into more detail on that as we go through the slides. But first, I think we should take a step back and talk a little bit about the conventional proppant pack testing. So conventional proppant pack testing utilizes typically 40 to 70 mesh sand, and it's sandwiched between two core platings. Typically, those cores are a standard laboratory core like Ohio sandstone, or they're a customer submitted core. Of course, with this technology, there's a lot of advantages. It's an industry accepted method, and there's a lot of historical data used for comparisons. But what we've also identified through talking to our clients and through this development work is that there is a long preparation and runtime associated with this style of testing, on average of 4 days, but it can be longer depending on certain parameters. According to literature, there's also a high variability between proppant packs themselves. And if the operator is changing, there's a high variability between laboratories as well, up to an over 80% variability. So of course, with all of that, the higher the longer times and using lab core, there's also a higher cost associated with this style of testing. So what we've done at Interface is we've taken that proppant pack and we've replaced it with our highly controlled porous media. And you can see that on the right-hand side, where we've replicated the proppant pack on our reservoir analog. And so what we've been able to do is really increase the repeatability of this testing. So we're seeing under 10% variability, and typically it's actually under 5% variability. We also have an 8 times faster turnaround using just one bench. From that image there, you can see that we're able to run 2 separate tests in parallel. So that really helps us to increase our turnaround time. We also have an over 50% cost reduction in this style of testing compared to traditional laboratory methodology. Also, due to the nature of microfluidics, we're able to really reduce the sample size that's required to under 250 milliliters of fluid. Just a single test takes under one milliliter of fluid. So because we've been able to really standardize our testing platform, there's a potential for aggregated statistics. And the results that you obtain today, they'll be comparable again in the future. So we've really taken out the variability of the proppant pack itself and replaced it with something that's highly controlled. So let's walk you through the reservoir analog design here. So you can see on the right-hand side, we have the CAD design of the analog. And what we've done is we've replicated the 40 to 70 mesh proppant size. So we have a 7.8 micron pore throat depth with 70 micron pockets spread throughout. This brings us to a porosity of about 22% and a permeability of 1 Darcy. So at Interface, we're able to highly customize these reservoir analogs. And in this case, our target was to replicate a 40 to 70 proppant pack on this device. When we're talking about the performance indicators, what we're looking at is measuring the pressure differential across the system. So initially, we measure the pressure drop of brine through the system to obtain our baseline. We then inject the polymer or the friction reducer through the system until we obtain a stable pressure drop. This is typically done for about 5 to 6 hours. And then we again flow brine through the system. So what we're looking at is comparing the final pressure differential of the system to the initial pressure differential. So that gives us a damage factor, or essentially a ratio of regain conductivity in the system. And from that, what we've done is we've created a relative regain conductivity value. So the values that we'll be reporting on today are a regain conductivity percentage. And just to quickly give an overview of key performance metrics. So of course, the main thing that we're looking at is the regain conductivity in the system, but there's also other insights that we're able to obtain throughout the testing. So we're looking at different things like time to stabilize, how long does it take for a friction reducer to clean up in our system, and then the change over time. So some friction reducers may start out highly damaging, maybe indicating certain solubility problems or injectivity problems. But as they go through the test, they clean up very well. So that's another thing that we look out for. And just to point out this image here, this is one of our regain conductivity analogs. And you can see in the little circle is an SEM image showing the replication of the proppant pack on our analog. All right, so I'd like to jump into some of our case studies. I'll start with the Ovintiv case study. And then once I've walked through that, I will go into Rockwater as well. So I'd just like to take a chance quickly to thank our partners. We really appreciate everyone who partners with us to help us develop technology like what I'm presenting today. So big thank you to them. All right, so just to give you an overview of the Ovintiv case study. The challenge that we were facing was to develop a method for friction reducer selection and optimization that is repeatable, fast, and cost-effective. So we wanted to be able to quantify the relative performance of friction reducers in a highly controlled method, at least as accurately as traditional methods. And through that, validate our new method against proppant pack testing. So what we were able to do is replace the high variability of proppant packs through our technology and isolate and quantify different variables that affect friction reducer performance, like concentration, temperature, brine salinity, and breaker. So with Ovintiv, we conducted a blind validation. And what we did was we screened 8 different friction reducers from 5 different vendors. And once we had completed that, we compared our results against conventional proppant pack data. So we were able to find a really strong correlation between the trends that we saw in our system and the values that were obtained using proppant pack. So what we have here is our results taken from this project, and the final value reported as shown in the bar chart at the below is the final reported value after 15 hours of stabilization. So what we found when we were running this test is that sometimes the final percentage, the final regain conductivity percentage, doesn't tell the whole story. So we've also plotted the performance over time. So for example, if you look at the 3 lowest performers, which in this case were FR2, 6, and 8, although they all have similar values, if you look at the trend over time, you can clearly see that, for example, FR8 took a much longer time to clean up. So certain insights into the performance over time may be helpful in ultimately selecting the friction reducer that is used. Certain friction reducers may have, they may both have optimal performance at the end of the runtime, but if you look at certain parameters, solubility, injectivity, maybe different viscosity effects, it really helps to determine which friction reducer would be optimal for field selection. Another thing that I want to point out here is the error bars on the final values. So you can see that we had very tight, repeatable data coming out of this project. When we further looked into the regain conductivity, we separated it into freshwater friction reducers and brine friction reducers. Looking at the freshwater friction reducers, you can see that all of the friction reducers that we used followed a similar trend, with FR1 outperforming FR6 and FR7. We also noticed that FR1 and FR7, they took the longest amount of time to stabilize, about 10 hours, whereas FR6 only took 5 hours. However, even though it stabilized the fastest, it was the most damaging overall. Looking at the brine friction reducers, looking at high salinity FRs such as FR3 and FR5, you can see that they resulted in a comparable final regain conductivity value. However, FR3 took 10 hours longer to stabilize and was more damaging in the first half of injection compared to FR5. Now moving on to Rockwater. So what we did with Rockwater is we really took this concept of using our technology for regain conductivity, and we wanted to see how we could use that for further optimization of the FR package. So I'll walk through different parameters such as brine concentration, powdered versus liquid FRs, and so on. So the first thing to note here is just the final regain conductivity values across the 6 FRs that we tested in this case. So we tested 6 different FRs with and without breaker. So looking at the final regain conductivity values, you can see that in the cases of 4, 5, 6, and 8, there was considerably higher damage without breaker. In the cases of 7 and 9, although the values are comparable, using breaker actually increase the amount of damage, at least looking at the final regain conductivity value. When we look at the trends over time, which I'll show you in the next few slides, you can see that although the final regain conductivity value may differ slightly, it may still be better to use breaker in this case. And I just want to point out as well that the breaker in this project is notated as E. All right, so looking at broken versus unbroken FR, you can clearly see that there's considerably more variation from the unbroken friction reducers compared to the broken friction reducers. And in all cases, broken friction reducer produced less damage when considering the entirety of the run than unbroken friction reducer. So we're also able to use this style of plot to evaluate key insights such as solubility of the FRs, injectivity problems, and long-term performance. Now, if we separate those same 6 friction reducers and we break it down into liquid versus powder friction reducer, we can also gain some insight into the different preparation methods and their impact on performance. So if we look at the liquid friction reducer in this case, FRs 5 and 6, they required less breaker to achieve the same level of performance as the powdered friction reducer. In the case of the powdered friction reducer, you can see that purple line that starts way down in the 30s, it exhibited a higher tendency for solubility challenges than any of the liquid friction reducers. So being able to gain insights like this may help you in your field decisions. So we also did an analysis on low versus high salinity. So in this case, we had 2 friction reducers, and we initially ran them in low salinity with and without breaker. So you can clearly see in both cases that the unbroken friction reducer, which is the solid line, resulted in the most damage. So we then took the broken friction reducer, which performed very well, and we put that into a high salinity API brine. So that API brine was 8.5% sodium chloride and 2.5% calcium chloride. We did see a minimal difference between the low and high salinity case, indicating that these 2 FRs had a pretty good salt tolerance. We did see a minimal change in FRB, a slight reduction in performance in the high salinity case. So another thing that we looked at was the time it took each FR to stabilize. So essentially the cleanup time. So in all cases, except for FR4, the broken friction reducer took considerably less time to stabilize than unbroken FR. Specifically looking at the case of FR6, you can see that there's a significant difference between broken and unbroken friction reducer. In this case, using breaker improved the cleanup time by 750%. So and what we found here is less time equals better performance. So just to summarize some of the outcomes that came out of these 2 case studies, we were able to isolate and quantify the variables affecting friction reducer performance, such as FR concentration, temperature, brine salinity, and breaker. We were able to do this in a very short amount of time. So we actually ran 20 regain conductivity tests in just 12 days. So compared to conventional proppant pack methods, this saved 2 months of laboratory time and more than 50% in cost. We were also able to demonstrate a method with less than 5% variability, providing more reliability and differentiation between the products compared to traditional methods of up to 80% variability. With that, I'd like to open it up to questions.
There we go. I'm back. Thanks for that, Jillian. That's very interesting results. Can you talk to me a bit about, you said we have a standardized porous media that we use today. How did we come up with that design, and why did we select that one?
Yeah, that's a great question. So typically at Interface, we work with highly customized analogs, depending on the application, the specific reservoir, or the well that we're working with. In this case, we wanted to create a standardized reservoir analog to really represent the proppant pack, to enable faster, repeatable screening. So what we did is we went through a series of different iterations of the reservoir analog design, all the way from including nanoscale features to the design we've now settled on, which is representative of that 40 to 70 mesh proppant pack.
Great, thanks. And I got a question here from the audience about temperature and pressure limitations. Can you just reiterate what those are?
For sure. So in this case, for regan conductivity specifically, we have been running these at atmospheric pressure, taking that up to 3,500 PSI, like our other testing is in the works. So we're currently running at 200 degrees Fahrenheit. But once again, we're working to bring that all up to the same level as our flowback and EOR offerings, which is in the 300 Fahrenheit range.
Perfect, thanks. Question here from Ray. What are the fluid and viscosity rate limitations?
So we currently haven't found limitations in terms of viscosities. We've worked with very high viscous, cross-linked, unbroken friction reducers in this project. So it would be interesting to have a project like that where we look at the viscosity ranges, but currently we haven't found an upper limit.
And we're used to working with everything from light oil all the way through bitumen. So our systems are very well tuned actually for these high viscosity applications.
That's correct.
And you showed an example there of FRs that performed well in a high brine situation. Did we have a chance to test any FRs that weren't so salt tolerant?
So we haven't specifically encountered any that are poor performers in high salinity. I think that the projects we worked with really, our clients are focusing on finding high salinity applications for their FRs. But I'm sure if we were to expand the test matrix a little bit, there would be some that wouldn't perform as well.
Yeah. And then just to expand a bit on sort of the customizability of the system, we've got a standardized porous media. How would we take into account the specifics of a customer's particular situation if they're not fracking with 4070, for example?
Right. So I think there's a lot of opportunity there, all the way from changing the permeability to represent different crush on the proppant itself. We could also look at changing the sphericity of the proppant pack. So there's really a lot of different applications depending on what questions are being asked.
And then the beauty of the system then, I guess, is you're able to compare the standard 4070 system against the new system to understand if you're helping or hurting your fluid system.
Yeah, that's right. We've actually done a similar project with different polymers where we looked at a range all the way from 1 Darcy down to 100 millidarcy. And you can really see that as you start to decrease the permeability, the impact on the polymer is substantial.
One more question here from Robert. Would you say that this microfluidic testing can replace the testing typically done in an FR loop?
So I think in an FR loop, I would like to say yes, that we could replace that testing. Our goal is to be a quick screening tool. So there may still be some value in using conventional testing, including the proppant pack and testing and so on. But what we're able to do by running these tests so quickly and so repeatably is to take a large test matrix. So maybe you're interested in 10 different FRs or different conditions, different breaker concentrations, and really identify the optimal performers in our system, helping you to have the best starting point when you go to other testing methodology.
Yeah, and just to add on to that, we're not able to actually measure friction reduction in our system, but we are able to quantify the damage that would be caused in the porous media. So we do see the need for additional testing beyond just what we do. I don't think this is a whole cloth replacement for all the other laboratory methods that have been proven over the years. One more question from Ray. Are you able to characterize the nature of the damage that may occur? For instance, strands of unbroken gel in the pore throats.
So we haven't specifically looked at this in this application, but I would say there is opportunity to include different imaging techniques that would provide insight into specific damage mechanisms. We do have access to a lot of different optical equipment. So I think that would be something that we'd definitely be interested in pursuing.
Yeah. And so, you know, I don't see any other questions coming in here, but one last thing, you know, you do your regain conductivity with interface fluidics, make that understanding. How do you typically recommend folks go on to learn more about their fluid systems and optimize those fluid systems after doing regain?
Right, so I think there is value in taking the learnings from our regain conductivity technology and then looking at maybe the impact of the mineralogy of the proppant itself. So I think there's an opportunity to really look more closely at the friction reducers we're using in the field. There's a lot of room for optimization when it comes to breaker usage, high salinity applications. So like I mentioned before, just really being able to screen through a wide range of parameters before moving into maybe using your core then and just a better design core test after our technology is used.
Excellent. Excuse me. Thanks very much, Jolene. And unless there are any other questions here, feel free to reach out, as I said, on the webinar at interfacefluidics.com, tweet at us, leave a comment on YouTube, and we will make sure we get back to you. So thanks again, and let's sign off here. Have a great afternoon, everybody.
Thank you, everyone.